There we are. Alrighty, lads and ladies, welcome back to Calc 2. Remind myself where we left off. I think we have cleared out partial fractions, right? We've pretty much nailed all the partial fraction stuff down to the wall. We're ready for the house to shake a little bit. So if I'm thinking correctly, today we're going to talk about section 7.5. We got study guide 1 up, and we've got 7.4 up. Both parts 1 and parts 2. 7.4 part 2, study guide 1 are due on the 27th. Okay, so let's do the thing. We're ready to do the thing. All right. Okay. So this, as always, is MAC 2312, section number 004, which is a Calc 2 file. And today is the 22nd of September, 2021. Today we're going to look at strategies for integration. Which is section 7.5.
Is this section on our exam?
Well, so this is kind of what I was saying the other day. Section 7.5 doesn't actually have anything new in it. There's no new technique, there's no new trick, there's no new problems in this. It's just a combination of problems from 7.1 through 7.4. The big difference is there's like in section 7.1, you know to do integration by parts on every single problem because that's the section on integration by parts. In section 7.3, you know to do trig sub on every problem because that's the section on trig sub. Section 7.5 is a mixture of all of those problems from earlier in chapter 7, so you can't infer which method to use. I would say yes, this is on the test, right? Because on the test, I'm not going to tell you use integration by parts or use trig sub. You're going to have to decide yourself what method you're going to use. And it's precisely that skill that this section is meant to train. Okay. So the big question here, let me just say here first, recall. Exam 1 is close. What date did we set for you guys? No, we did set it. 27th, Monday, yeah. And you can take it either online here with me, and you'll be using Zoom on your phone and Honor on your PC, or you can take it at the testing center. Either way, the test is going to be in Canvas. We went through all those details. I just want to remind you when is the exam and how to do this. If you're going to take it at the testing center, you need to send me a Canvas message. So I can book you, so I can get you an appointment. Right, because the testing center, they get busy. They don't always have room for everybody to just walk in without any sort of appointment. So if you want to take the test at the testing center, instead of doing all the Zoom stuff and Honor stuff with me online, you can do that. That's okay. Okay. So getting to the material, the big question for today is, given a random integral, say random, whatever, random integral, how do we know which technique to use? should I use, integration by parts or trig sub or partial fractions or something else, The book has a fairly reasonable algorithm that I'm going to distill down to its absolute essence for you, which is what I will write here. And then I will show you the algorithm exactly as it is in the book in all of its long, gory detail. And then we will solve some problems. So here's kind of my suggestion. First, simplify the integrand algebraically if possible. All right, like if you're asked to integrate something like x squared minus 2x plus 3 over x, you can split this up as x squared over x, which is just x, minus 2x over x, which is just 2, plus 3x to the negative 1. All right, this is just for example. All right, maybe looking at this thing, it's not entirely obvious how to integrate it, but looking at this thing, it is. All right, we know exactly how to integrate this. Each piece is just a power rule thing. Second, I would say if you don't see a way to simplify it into something that you know how to integrate, you could also do this with trig functions, right? Like if I gave you secant divided by tangent squared or something like that. You write secant as 1 over cosine, tan squared as sine squared over cos squared, and then you flip and clean up. If you don't see anything like that, which you can do, then you should look for, say, simple substitution, like u sub, right? Is there an inner function? Now we know for this to work, you have to have the appropriate piece for the differential, right? If you want to sub u equals x squared, you need an x floating around in your integral that you can cancel with the du piece, or that you can group with the dx piece. So look for a simple substitution, which is usually going to be subbing for the inner function, but make sure that you can actually make that substitution go through. Make sure you have the pieces you need for your differential. If you don't see a simple substitution and there is no algebraic simplification you can do to clean things up, then you want to start kind of thinking about the shape of the integrand. Is it something that looks trig sub-y? Is it something that looks partial fractions e? Is it something that looks, like it could be written as a power of sine times a power of cosine? So the way the book says this is classify according to form. So here, for example, if you have a polynomial times exponential or sine or cosine, something like this is going to be IBP, integration by parts. Or if you have something like a square root of some quadratic, that's probably going to be a trig sub thing. If you have a bunch of trig functions, right, you're going to use the 7.2 stuff. I don't know how much of this we want to say. I'll just leave it as this, etc. Right, so try and see if that integrand looks like one of the integrands from the previous sections. Okay, and then you would apply that method. If none of this stuff appears to be working, then you want to look harder for a substitution. Look for a less simple substitution. Maybe like a rationalizing substitution or something like that. All right, this is basically the gist of it. So first, try to simplify algebraically. Then see if you can do it with U sub. Is there a U sub that would work? If not, then you want to try and break it down according to the other techniques that we've seen. So you know if you have any polynomial times e to the x or polynomial times sine or cosine, anything like that, it's always going to be integration by parts. You know, if you have a square root of x squared plus a squared or a square root of 1 minus x squared, anything like that, it's going to lean towards trig sub. You know, if you have a rational function where the degree of the top is smaller than the degree of the bottom, then you're going to use partial fractions and so on. And then if you don't see any of this, then maybe trying to force a less obvious substitution in is a good idea. So this is kind of how the thing exists in my brain. Let me show you how it exists in the textbook. So certainly, first and foremost, you do need to know all of these things. Right? These are all the basics. You'll notice that a few things have been added from the version of this that exists in chapter 5 and 5.4. These bottom two rows, I don't memorize these. When I need these, I cook them up. But certainly up through item 18, you need to know, right? So on the test, I will be assuming that you know these. So straight up by heart, don't need to do any work. You know this shit cold. And you will be free to use these, right? You don't need to prove anything to use these. You don't need to show work for these. If you run into the integral of cotangent, you can just tell me it's the natural log of the absolute value of sine. Or if you run into the integral of 1 over x squared plus 4, you can tell me it's 1/2 times the inverse tangent of x over 2. I won't give you a hard time for that. So here's their algorithm. Simplify if you can. Right? This can mean distributing and rewriting as powers. This can mean cleaning up. Well, that's almost exactly what I said, isn't it? I said secant over tangent squared. Trig functions, right? You know that tangent and secant are defined in terms of sine and cosine, so try to clean them up. You'd be surprised how much you can do. Or if you have something like sine plus cos all squared, you can FOIL it out and then break it up into pieces. If there's no obvious simplification, look for a simple substitution. Right? Like here, you've got an x squared minus 1 downstairs, and you've got an x upstairs. So if you sub for x squared minus 1, then du is going to be 2x dx. That'll eat up this x and this dx, and you'll be left with a 1 over u integral with a 1/2 out front. The big deal when you're looking for a substitution is that you also need the derivative of your substitution, right? So if you're going to sub u equals something, then you need the derivative of that something floating around, or at least something close to it. And then classify according to form, right? So if you got trig functions, then you're going to use the mechanisms from 7.2. If it's a rational function, a ratio of two polynomials, then you're going to use the mechanisms from 7.4. That may involve some polynomial long division if the rational function is not proper, or just straight up partial fractions if the rational function is proper. There are a lot of things we can do with integration by parts. And the first thing that comes to mind is exactly what I wrote down. You've got like a polynomial or a power function times exponential or trig or log function. Any of those will always be done by parts. There's other stuff that's done by parts too, right? Like just straight up inverse functions like cos inverse of x or tangent inverse of x or the natural log of x. All of those are done by parts. If you have square roots of quadratics, then we're looking at trig sub probably, right? Especially if it's a square root of something like x squared plus a squared or a squared minus x squared, something like that. Sometimes, if you've got a root of a linear function, you can sub like u to the n equals the inside, or u equals the nth root of that thing. to get rid of the square. Doesn't always work. And then if nothing else has done the job yet, just run back through it, right? Look a little bit harder. Sometimes the algebra you need to do is not as obvious. Sometimes the substitution you need to do is not as obvious. Integration by parts, never a bad idea, right? If you're absolutely dead stuck on a problem, you don't know what the fuck else to try, you can always try IBP. Just pay attention to whether the output is better or worse than the integral you started with. Manipulate the integrand. This is just more like simplify algebraically, right? So this is a great problem. 1 over 1 minus cosec, because at a glance it doesn't look like anything we know. But if you multiply by 1 plus cosec over 1 plus cosec, it turns into something that's quite easy to integrate. This is kind of like multiplying by the conjugate or rationalizing the denominator. And then finally, they say you can relate it to previous problems. So remember the tan squared secant integral, one of the ways we did that was by parts. The other way we did that was by turning it into secant cubed and secant, odd powers of secant. And of course, you can combine methods like making a substitution, then doing partial fractions, stuff like that. All right. So this is the book's full description of the strategy. This is how I usually think about it. Do some algebra. That doesn't jump out at you. Look for a basic substitution. If nothing like that is going to work, ask yourself, does this look like it belongs in any of the sections we've covered? Does it look like an IBP problem? Does it look similar to the shit we did in 7.1? If not, does it look similar to the shit we did in 7.2? If not, does it look like the shit we did in 7.3? And so on. And then if none of that works, try a more creative substitution, like one of those rationalizing substitutions, or try subbing and then doing something else, like substitution, then integration by parts, substitution, then partial fractions. And they just say, try again if you're stuck. So we can work a few of their examples here. Let's start with that, tan cubed over cos cubed. So who can tell me what we should do with tan cubed over cos cubed? Over cos cubed, yeah. Who's got a suggestion?
Simplify a tan out and a cosine out.
What do you mean by out?
Like make it towards tan squared x and then another tan. And then do that for a cosine too.
We could do that. We could do that. Tell me in your mind where this is going. So you guys play chess? Anybody play chess? Sorry, I know I'm derailing the conversation a minute. We'll come back to that, Alex, I promise.
Yep.
So when you play chess, right, one of the first steps towards actually learning the game properly is realizing that you don't just want to think about your goals, right? You don't just think about like, ooh, the king's there, let me go get the king this way. You have to ask yourself every move, if I do this, what are the possible responses, right? What could my opponent do in response? That's the step 0 to getting good at chess. Same thing applies here. So let's come back to that. If we pop out a tangent here and a cosine here, I think I know what you're thinking of as the next step, but what are you thinking would be the next move then?
I was thinking you switch the tan squared to secant squared and then do that to it, but I don't think it would change much.
Well, we could do that, right? And I think if you did that upstairs, you might get somewhere useful. But remember, so the reason that would be useful is because you can split a fraction up over its numerator. So if I have like 1 minus secant squared or 1 plus secant squared upstairs, something like that, secant squared minus 1, I can split that up as 1 over cos cubed minus secant squared over cos cubed. That sort of thing we can do. But we can't split up fractions over their bottom like that. If I rewrite the cos squared there as 1 minus sine squared, I can't take the top over the 1 minus the top over the sine squared. That doesn't work. So splitting it up over the top after popping out a tangent would be a valid approach. Let's try it. I'll be honest, this is not what came to mind for me, but we can try it. So this would be tan squared x times tangent x. One of the things you'll learn, and probably you're already learning, is that many of these problems can be solved multiple ways. You're kind of wandering through a forest and there's many, many paths. Some of them lead to the correct place, the answer, some of them don't. Some of the ones that do get you where you want to go are longer than others. So I pop out a tangent in the top, I write it as tan squared times tan, and then that first tangent I can rewrite using my Pythagorean identities. I know tan squared plus 1 is secant squared, so tan squared is secant squared minus 1. Gotta have these trig identities ready to go. And then I think the idea is that we could distribute the tangent and split the integral up. Is that what we're thinking? So that would get me secant squared times tangent over cos cubed minus tangent over cos cubed. And we want to ask ourselves, are things getting nicer? Am I getting to a place where I can cancel stuff and stuff will go away? If I wanted to attack this or this, I'll tell you what I would do. I would rewrite it all in terms of sines and cosines, like the secants and tangents, because I have a cos cubed downstairs. I'm hoping something will cancel or go away. Same thing here. So when we look at this, maybe we want to rewrite as sines and cosines. And that tells me something. If I would solve either of these by rewriting as sines and cosines, maybe I could have just solved this by rewriting as sines and cosines. Maybe we want to do that from the start. So we walked a little ways down this path, and we saw that while it might be fruitful, this looks like it might be going where we want to go. The thing we would need to do to start kind of turning in the direction we want to go is something we could have done from the very start. So instead of pursuing this path further, let's run back to the start and see if there's a shorter path by doing this thing we were going to do anyway to the original problem. Let's try it. Integral tan cubed x over cos cubed x dx would be big integral. Tan cubed is sine cubed over cos cubed. And the downstairs cos cubed is just cos cubed. And remember how fractions work, right? The top chilling, and we multiply by the reciprocal of the bottom. So that's going to be sine cubed x over cos cubed x times 1 over cos cubed x dx. Which is sine cubed over cos to the 6. Any ideas what we could do from here?
Use some trig identities.
There's some trig identities we could use. Let me ask you this. So this is definitely a trig integral, right? What kind of trig integrals do we know how to do?
Like sine squared, cos squared, secant. Oh, we can turn the cosine into secant,
Yeah, there's
like 1 over cosine.
two big families of trig integrals we know how to handle. Powers of sine times powers of cosine. And this doesn't clean up into one of those, right? There's no way to make this cos to the 6 downstairs go away. So I can't turn this into a power of sine times a power of cosine. What's the other big family of trig integrals we know how to do?
Can't you do 1 minus sine squared x
Uh,
and then put that all to the third power?
we could rewrite the bottom as 1 minus sine squared, all cubed. Yep. But focus on the question I'm asking just for a second. There's two big families of trig integrals we know how to do. Powers of sine times powers of cosine. And what's the other big family that we know how to handle?
Tangent and secant.
Yeah, powers of tangent times powers of secant. I cannot write this as a power of sine times a power of cosine. When I put everything in terms of sines and cosines, I have a cos to the 6 downstairs. That ain't about to go away. So we should see
Oh,
if
we
can
can
write
do,
this.
is it tan cubed x, over secant cubed?
So let me make a few comments here. This can't be written as some power of sine times some power of cosine. So maybe as a power of tangent times a power of secant. Whoop. Remember what we said back in section 7.2, any trig integral can be rewritten as a combination of these and these. And we know how to handle powers of sine, powers of cosine, powers of tangent, powers of secant. So instead of trying to sneak our way around it, we should take this integral, which is definitely a trig integral, and try to put it into one of these forms from the trig integral section. We see we cannot write it as the first type, so we should try to rewrite it as the second type. And in fact, it's easier to see from here what that is. So we're going to write this as, I've got my sine cubed over cos cubed, just coming back one step there, times 1 over cos cubed. I'm going to write this as tan cubed times secant cubed. And this is something I definitely know how to do, right? Every integral of this form, I know how to do. And if we're careful, we could have spotted this right away, right? Just looking at the original tan cubed over cos cubed, I could have said, okay, tan cubed is tan cubed, 1 over cos cubed, that's secant cubed. So this is tan cubed times secant cubed. Now, I like that we tried other stuff, but this is going to be the fast path, right? Maybe we could get there going this first way, right? If you split each of these up and rewrite each of them as their own secant tangent thing, then definitely we can get there. If you were to start trying to play games with this, like factoring or using trig identities, you could eventually get it to something like this or combinations of things like this. But once you realize it can be written like this, you should know immediately to latch onto that because you know how to solve any power of tangent times power of secant. And then, yeah, maybe some Pythagorean identities will be useful. Let's see. So of the tangent secant integrals, which category does this fall into? Remember, we had cases for each of those big families. Which case is this integral in? Do you remember what those cases are?
Tangent is odd here.
Very good. The power of tangent is odd. The cases for the secant tangent integrals were if the power of secant is even, you're going to sub for tangent, right? You set 2 secants aside, sub for tangent. If the power of tangent is odd, you set aside a secant tangent and sub for secant. So here, the power of tangent is odd. So we're going to try to sub u equals secant x. And in order to do that, I'm going to rewrite this as tan squared x times secant squared x times secant x tangent x dx. So my goal here is to sub for secant. Here's the piece that I'm going to use for my differential. So you set aside a secant tangent, right? That will be your du. But then you need to rewrite this in terms of the secant function. So you can call it u. And tan squared is secant squared minus 1. So here we are ready for the substitution. U is secant x. Du then is secant x tangent x dx. So this is going to be integral u squared minus 1 times u squared times du. All right, this piece is your du. Du is secant x tangent x dx. And these pieces are u squared minus 1 times u squared. So we tried a few things before we ran into one that we knew exactly what to do with. But once we found that, the integral is quite easy. This is the integral of u to the 4 minus u squared du, which is going to be u to the 5 over 5 minus u cubed over 3 plus a constant, which is the secant function. So it's the 5th power of secant over 5 minus the 3rd power of secant over 3 plus a constant. So I think one of the big things that's nice to think about in this section is what sort of integrals do you like know how to solve immediately? There's lots of them, right? Pretty much all the like prototype problems from the previous sections. Once you're able to turn a kind of challenging looking integral into one of those, you know you're home free. So you want to make sure you have that library of functions I know how to integrate very clear in your head. Not just the stuff from that table, but also the stuff that you like immediately know what to do from each one of the sections 7.1 through 7.4. As soon as you get an integral into one of those forms, you just blast it. Questions on this guy?
So you substituted the tan squared to secant squared minus 1.
Yeah, I used the trig identity. Tangent squared plus 1 equals secant squared. I rewrote that as tangent squared equals secant squared minus 1, and then plugged in for tan squared. Identity here. You know from sine squared plus cos squared equals 1. If you divide everything by cos squared, you get tan squared x plus 1 equals secant squared x. And then subtracting 1 from both sides, you get tan squared x equals secant squared x minus 1. And we want to have these trig identities like so clear in our mind that we don't even have to think about this. If you are unsure, like, oh, is it 1 minus secant squared or secant squared minus 1? You can always derive all of those starting with sine squared plus cos squared equals 1, like I did here. No cheat sheets for the test, no. Definitely not. It is the case that mathematics builds, right? we have to remember what we learned in our previous classes in order to move forwards. If you're always looking for references, then it's going to slow you way down on problems. So no cheat sheets. We do have to learn this stuff. If you're having a hard time baking things like these identities into your brain, I know a lot of Calc 2 students do struggle to remember their trig identities. First, let me say, each time you need one, like here, go through this process of deriving it. It took all of 2 seconds. And if you do this 10 times, you'll remember it. You'll remember it in a way that you'll never, ever forget it. If you want to remember it in a way that you will forget it, use flashcards. Flashcards will at least get them in your head for the purposes of the test. And if you want to, the moment you start your test, do like a memory dump where you just write down all the stuff that you've crammed into your brain that you're worried about forgetting, like your trig identities or your unit circle, that sort of stuff. You can do that. but we cannot bring any prepared sheets into the test. Other questions? Oh, I will say this about cheat sheets. Let me back up on that just a little bit. On the one hand, I want you guys to remember the material from your previous classes. All right, so I have no cheat sheets. On the other hand, when you take tests in the classroom with me, I guess it's been so long since we've done an in-person class, probably none of you have ever taken an in-person class with me. You can raise your hand and ask a fucking question, right? You can do that. You can go, hey, do I have this identity right? Or, something like that. And I'll answer you. I will. So if you're taking the test with me online, you can ask for help. You can be like, oh, I'm a little bit stuck on this. I think I need to do this. Am I doing this correctly? Or, is this identity with a plus or a minus, that sort of stuff? I'm happy to answer during the test. So the worst, if you're really stuck on something, you're not sure what to do, and it's bothering you, the sort of thing that you, for example, might want to have a little cheat sheet for, you can ask me, right? Just ask for help, and I will give you as thorough an answer as I can without violating my ethics.
When you say ask you, since like it's on Zoom too, you want us to like give you a chat or like call your name in the middle of the Zoom?
Yeah, so in Zoom, there's like a raise hand feature. Just raise your hand and I will come to you and ask you what's up. Yeah, you can look for it now, right? In fact, in advance of the test, go ahead and look at your reactions here in Zoom. You see there's a little reaction button. One of those is a raise hand.
And also that won't flag our honor lock if we're on our phone clicking on Zoom.
It will, but I'm the one who reviews the honor log. So, if I look at all the flags, and if it's just you talking to me, that's okay. Yeah, it will flag honor lock, but you don't need to worry about it. Okay, let's look at another example. E to the root x. This is fun. Okay. Any thoughts on this one? There really isn't any algebra simplification we can do here, right? There aren't like multiple pieces to play with or rewrite or use identities on. There's nothing to distribute or factor or FOIL or cancel. So I would say that step one in our algorithm, he's out. We're not going to get here by just rewriting the integrand. So what's our next step? What should we be looking for here?
Try something for the square root of x.
That's the idea. Yeah, if this was just an x or a u instead of a square root of x, that would be nice. So you can try subbing u equals the square root of x, which means, so that's x to the 1/2, right? I write it that way because I need to calculate du, which will be 1/2 times x to the negative 1/2 dx. Now, that means this piece would become e to the u, which is nice. But what about all this stuff? I can't just ignore this, right? This is important. This is what relates du to dx, and I know I need to replace this dx.
The 1/2 comes out front, and then that's 1 over root x.
So it's not a 1/2 that's going to come out front, but you're right about x to the 1/2 being 1 over root x. So it's going to be 1 over 2 square roots of x dx, right? That's what this 1/2 and this x to the negative 1/2 become. It's true that there's a 1/2 here, but that 1/2 is multiplying the dx, and I need to replace the dx by something. So if we were to solve this for dx, that would mean 2 square roots of x times du is equal to dx. So this integral would start to look like, I'll just rewrite it here first, e to the square root of x dx. If I start plugging this substitution stuff in, it's going to look like, okay, e to the u, e to the square root of x, and then dx is 2 square root of x du. But this is a problem, right? What's wrong with this integral?
You still have different variables.
Right.
What if
Can't
we
have
solve for
different
x?
x's. Very good. In fact, you don't need to solve for x. You know that the square root of x is u. Right? So it's even better than that. You don't even really have to solve for this. We got super lucky here in that this kind of extra piece that's left over is exactly equal to u. So this is e to the u times 2u du. So what you'll see is it's actually a 2 that comes out, not a 1/2. And then what's left over, we would normally write as u times e to the u du. And what do we do from here?
Integrate by parts.
Very good. This is a by parts problem. All right, I'm going to use capital U and capital V because I've already used lowercase u. So what should I pick for u? What should I pick for my capital U, the u in my integration by parts?
U.
Yeah, this piece, right? Follow your Lipet rule. Are there logarithms here? No. Are there inverse functions here? No. Are there polynomial functions here? Yes. U, this thing on its own, is a polynomial, which means dv has to be everything else. So d capital U is d little u, and v is the integral of e to the u du, which is e to the little u. So this piece, little IVP table, this piece would become 2 times big parentheses. I'm about to replace this integral by a difference of 2 terms. So I need to make sure that this 2 goes to everybody. And that would be this times this minus the integral of this times this. That's 2 times u e to the u minus the integral of e to the u is e to the u. You can slap your plus c out here like that. You can distribute the 2 if you want. All right, so this is not too bad. The hard part about this, I think, right, calculating the differential and knowing what to do with it. There is a way to avoid all of this and go straight to this. Does anybody know what that is? A better way to implement that substitution. Instead of saying u is the square root of x, I could say u squared is x, right? If x is equal to u squared, then this would just become e to the u. And this lets you calculate the differential in terms of the new variable u. Taking differentials here, you find 2u du is equal to dx. So then plugging this in, integral e to the square root of x dx becomes integral e to the square root of u squared times 2u du, which is the e to the u times 2u du that we ended up with, but without all the the hard work of fucking around with the differential. So think about different ways you can write the same substitution. U equals square root x is the same as u squared equals x. And as long as you know how to calculate this differential, you can save yourself messing around with the weird powers and solving for dx, all of that. It can be done very, very smoothly, very, very quickly.
Why do you use u squared?
Saying u squared equals x is just another way of saying u equals square root of x. Are we on the same page there? These two actually define the same relation. Right, if you square both
Okay,
sides
thank
of
you.
this, you get this.
Yeah, thank you.
And then the reason to do it this way instead of that way is because it's you just have to plug in for dx now. Right? I didn't have to solve for dx or rewrite anything. Here, when we did it the first way, I had this like weird integral with a mix of different variables, and I had to be very careful and remember to replace this by its equivalent form in terms of u. Here, I didn't have to do that because I already have the differential in terms of the variable u. I guess we could point out that this line right here says the same thing as this line right here. You guys see that? Because the square root of x is u. This says 2u du equals dx. 2u du equals dx. U is the square root of x in the purple sub. So yeah, look for substitutions and look for ways to make substitutions nice. The reason I anticipated the substitution being a little weird is because there's nothing here for me to group with the differential, right? I wouldn't call this an obvious substitution because the derivative of this inner function isn't floating around in there anywhere. I kind of had to force it in. All right, let's keep going. Yeah, we can try some partial fractions on this. We can talk about this real quick. This one. There's some other exciting problems in the exercises I want to look at, so I'm going to jump down a little bit after this. Let's x to the 5 plus 1 over x cubed minus 3x squared minus 10x. All right, what do I do with this? No, so there's a question that came to me in chat. Would you lose points on the previous problem for doing it the first way? Nope, as long as you get through it correctly. But I think it's easier to get lost going the first way. When you calculate that differential and you're like, what do I do with this? It can be a little trickier. But no, if you were to go through it the first way, like we did in purple on the last page and get to the end, then credit where credit is due, you solved the problem.
I don't know if those would do anything, but I would factor out an x from the bottom.
We can factor an x from the bottom. That's an option. Before we start moving in that direction, what kind of function is this?
This looks like a partial fraction.
This is a rational function. The integrand is rational. Now, before we get into any 7.4 stuff, we should first look for an obvious substitution. Like, can I sub for the bottom? Can I sub for x squared? Would anything like that make life easier? Well, if you sub for the bottom, the derivative is 3x squared minus 6x minus 10, which is definitely not the top. It's not something I have floating around here. So subbing for the bottom is a bad idea. What about subbing for a power of x? Well, subbing u equals x never does anything. That doesn't change jack shit. Subbing u equals x squared would be hard here because I have these odd powers of x. And subbing u equals x cubed would also be hard for a few reasons. I don't have an x squared that I can factor out from the top. It's my differential. And I don't know how to write x to the 5 as a nice power of x cubed. So basic substitutions won't work here. Is there any sort of algebra simplification I can do? Or can I just jump straight into
Factor,
partial fraction?
factor out an X and maybe factor out the bottom.
We could try to factor the bottom, that's true. It's true. Yeah, Coburn's got it in the chat. The degree of the top is larger than the degree of the bottom. In other words, this is improper. This rational function is improper. So we need to do some long division. That's the algebra simplification we can do here. So before we start factoring the bottom, which we will want to do when and if we get around to any PFD, we need to rewrite this as a polynomial plus a proper rational function, because right now it's not proper. The top has a larger degree than the bottom. So what we're going to do is we're going to divide the top by the bottom. I've only had a few examples of this, so I think it's a good thing to take a look at it. Remember the way this is done. You pay attention just to the lead terms. So I ask, how many times does this go into this? Ignoring all the other stuff. How many times does x cubed go into x to the 5?
One time.
Yeah, or maybe another way I should say this is, it's true that 3 goes into 5 once, but we're talking about powers here. So what must you multiply x cubed by in order to turn it into x to the 5? Yeah, very good, x squared, right? X squared times x cubed is x to the 5. So he goes in there x squared times. Right, so and I'll say that again. You're looking for, you ask, what must I multiply this by in order to turn it into this? Or what is this divided by this? And that's x squared. Then you take this x squared and you distribute it to all 3 terms here. X squared times x cubed is, by design, x to the 5th. X squared times negative 3x squared is minus 3x to the 4. And x squared times minus 10x is minus 10x cubed. You put that whole thing in parentheses and you subtract it from the line above. And we're subtracting 2 polynomials. So you do termwise. X to the 5 minus x to the 5 is 0. There is no x to the 4 term here. So 0x to the 4 minus negative 3x to the 4 is positive 3x to the 4. There's no x cubed term here. So 0x cubed minus negative 10x cubed is positive 10x cubed. And then 1, there's no constant down here. So 1 minus 0, it's just 1. Is everybody comfy with this first little loop of the long division algorithm? Are there any questions about where this came from or where this came from? Okay, then we just do it again. So now I ask this lead term, what do I need to multiply this by in order to turn it into 3x to the 4? So x cubed times what is 3x to the 4?
3x.
It's going to be an x. Yeah, we also need the 3. Yeah, so plus, so we write a plus 3x up here. And then I take just this 3x and I multiply it by this whole thing. So 3x times x cubed is, by design, 3x to the 4. 3x times negative 3x squared is negative 9x cubed. And 3x times negative 10x is negative 30x squared. And then you subtract one row from the other. 3x to the 4 minus 3x to the 4 is 0. 10x cubed minus negative 9x cubed, careful with your signs, is 19x cubed. There is no x squared up here, so 0x squared minus negative 30x squared is plus 30x squared. And then there's no x's in either. There's only a constant up here, so 1 minus 0 is plus 1. All right, we're almost done with the long division. What do I need to multiply x cubed by to turn it into 19x cubed? That's 19. So I wrote a plus 19 up here. And then we would distribute. So this is going to be 19x cubed. 19 times -3. Let's see, 20 times 3 would be 60. This is 3 less than that. So 57. That's -57x cubed. Sorry, x squared minus 57x squared. Now positive 19 times -3. 30 plus 27, yeah. And then 19 times -10x is minus 190x. And subtract the rows. 19x cubed minus 19x cubed is 0. 30x squared minus -57x squared is 30 plus 57 is 87x squared. There are no x's up here, so 0x minus -190x is plus 190x, and 1 minus nothing is 1. So this is the long division done. And this is a kind of a nasty one. The result, what we've learned here is that x to the 5th plus 1 divided by x cubed minus 3x squared minus 10x is equal to this polynomial, x squared plus 3x plus 19 plus this remainder, 87x squared plus 190x plus 1 divided by this divisor, x cubed minus 3x squared minus 10x. This is what we've just learned with that long division. So the integral of x to the 5th plus 1 over x cubed minus 3x squared minus 10x dx. I'm starting to wonder if they intended us to actually do this problem, is the integral of x squared plus 3x plus 19 plus 87x squared plus 190x plus 1 divided by x cubed minus 3x squared minus 10x dx. So this was an improper rational function. In order to get started, we had to do long division. That gives us a polynomial, which we know how to integrate, plus a proper rational function, which we, in theory, know how to integrate. So from here, you do partial fractions on this piece. And for that, you would want to factor the denominator. I'm not going to run all the way through it. I think I'll stop at the PFD setup here because the numbers for this example are pretty gnarly. But that denominator, this is x times x squared minus 3x minus 10. And then let's see, does that factor nicely? -10, -3. Yeah, 5 and 2, right? So this is x times x minus 5 times x plus 2. So your PFD setup would look like 87x squared plus 190x plus 1 over x times x minus 5 times x plus 2 equals a over x plus b over x minus 5 plus c over x plus 2. So we step aside from the integral and just go back to doing more algebra, right? we would clear out the denominators, solve for a, b, and c, and then plug that whole thing back in here, and then we would know how to integrate. Now, a, b, and c here could be quite nasty. I'm not going to go ahead and wrap it up because it's burned enough time on this, and these partial fractions things can be quite time consuming. But this is the strategy. Are there any questions on what we've done here or how you would finish this problem? Feeling good?
When is it on partial fractions that we end up with the top having like ax plus b? And like not just simple a, b, and c.
Right.
So wouldn't we have an extra power?
Well, it's when you have an irreducible quadratic factor in the denominator. So like if this thing, x squared minus 3x minus 10 didn't factor, if this was something like x squared plus 1 or x squared plus 2x plus 5, something like that, an irreducible quadratic, then you would have a over x plus bx plus c over that irreducible quadratic. So the question there was, when do we end up with stuff like, you know, ax plus b over something? When do I have a linear term upstairs in my partial fraction setup? That's if you have an irreducible quadratic factor downstairs. We can go hunting for something like that. Let's see. So there's a fun discussion in here. Can we integrate all continuous functions? This is a non-trivial question. And the answer is, in theory, yes. In theory, you can take a definite integral of any continuous function, but indefinite integrals are slightly different. Indefinite integrals, you're trying to find an antiderivative. And that's true. That's the way we evaluate definite integrals. But when we say the integral exists versus being able to calculate it, it's very different. So there's lots of stuff for which we can't find an antiderivative. All of these are quite famous integrals that you can't solve. Not just like you don't know how to solve, like cannot be solved. There is no simple function whose derivative is e to the x over x, or whose derivative is 1 over ln x. There's some shit we just can't do. I will show you how to do these later in the semester. It requires something called power series, but there's no closed form. There's no finite length expression for any of these. Fun discussion. So we're asking, when do we end up with a linear term in the partial fractions? And the answer is when you have an irreducible quadratic. So I think we've looked at a few things like this. I can show you just one more briefly. Number 12 is an example of such a problem. Paper. And there's a few others in here that I would like to look at with you. Cubed plus 3x. And I probably won't do this whole problem either because we've done a couple of these in class, but I can remind you when that sort of stuff shows up. So this is rational. 2x minus 3 over x cubed plus 3x is a proper rational function. It's rational because it's a ratio of polynomials, and it's proper because the degree of the bottom, 3, is bigger than the degree of the top, 1. So right away, we would jump into the PFT. Factoring the bottom, I see that this function is 2x minus 3 over x times x squared plus 3. X squared plus 3 has discriminant. You guys remember the discriminant of a quadratic from your college algebra days? B squared minus 4ac. Here b is 0, so that's 0 squared minus 4 times a is 1. C is 3. This is negative 12, which is less than 0. Therefore, this is an irreducible. Cannot be factored over the real numbers. So anytime you have an irreducible quadratic factor downstairs in your partial fractions problem, that term will need a linear numerator. So I'd have a over x from this guy, and then bx plus c over the irreducible. So you need to factor the denominator as much as you can. And if there are any quadratic pieces which cannot be factored, and I don't mean like the factors are nasty, I mean cannot be factored. The factors are not real numbers. The way you test for that is with the discriminant. If the discriminant is negative, then quadratic is irreducible. In that case, you give a linear numerator in the PFD setup. All right, and from here you would proceed just as we did in the problems in our previous lectures. Clear out the denominators, use the Heaviside trick to get as much as you can, and then equate coefficients to get everything else. So proceed as normal. All right, let's look at some more. Let's see if we can come up with the strategy to integrate some other stuff. How would you do number 2? This is parentheses 3x plus 1, all raised to the constant power square root of 2.
Sub 3x plus 1 with
Very
you.
good. Very, very good. So the square root of 2 power is a nasty power. You can't like FOIL that out, right? It's an irrational power. Good luck. But the inside is nice and simple. 3x plus 1 is a linear function. So you can always substitute for a linear function and it's never going to cause you any trouble. So again, I'll just write down the first few steps here. Here we would sub u equals 3x plus 1, because then du is just 3 dx. That's not bad. The other thing we need to do is change our bounds. Remember, anytime you make a substitution in a definite interval, you must change your bounds. When x is equal to 0, u is equal to 3 times 0 plus 1, which is 1. And when x is equal to 1, u is equal to 3 times 1 plus 1, which is 4. So the new integral here would go from 1 to 4. 3x plus 1 to the root 2 is now u to the root 2. And dx from this is 1/3 du. So you have times 1/3 du. So 1/3 comes out. Integral 1 to 4 u to the root 2. Why is this nicer than the thing we started with? How do you evaluate this integral? What rule can I use here that I can't use here? The very first rule you ever learned for integrals. Way back in Calc 1.
Powell.
Yeah, you can use the power rule. The square root of 2 is just a constant. So when you integrate u to that constant, you get u to that constant plus 1 over that constant plus 1. It's not a nice number, but you can do it. So at the end of the day here, this is 1/3 times 4 raised to the root 2 plus 1 over root 2 plus 1. minus 1 raised to the root 2 plus 1 over root 2 plus 1, which is 1/3 times. Well, there's nothing you can do with 4 to the root 2 plus 1. It's just 4 to the root 2 plus 1. And then 1 to the root 2 plus 1, that's just 1. So this would be correct. You could also factor out the 1 over root 2 plus 1 if you want. Right? This is 1 over 3 times root 2 plus 1 times 4 to the root 2 plus 1 minus 1, like this. Any of these would be acceptable. Oh, but it's not bad. It's a simple use of. There's a really nice inner function. That inner function is linear. You can always sub for a linear function. Those substitutions will always go through because the differential is always going to be a constant. Just remember to change your bounds. Remember on the exam, this is a requirement. You must change your bounds when you make a substitution in a definite interval. Questions on this?
Would the answer above the final be acceptable?
This would be
That-
acceptable. Yep.
yeah.
I would like to see that you know that any power of 1 is 1. So, you know, if you gave me this, I probably wouldn't take points off, but I would make a little note here. Okay. What else can we do? I'd like to look at, we haven't done much of the way of trig sub with definite integrals. There's also one particular flavor of problem that I want to share with you that we haven't seen yet. You see there's many, many things here for you to practice. And if you practice all of these, you'll get really good at them. It won't be bad. Let's look at number 70 here. I like these. We don't have time. 10:42. Oh, we don't have time to do both. Okay. Take a quick look at 70, which is 1 over 1 plus 2e to the x minus e to the minus x. This is not a rational function. Let's be clear about that. The e to the x messes it up, right? These are not polynomials. But there is some fun stuff I can do with this. So when you look at this, what does your brain do? What do you want to do with that? What makes this feel not obvious or different from other problems we've seen? The e to the x's, right? We've got all these e to the x's in kind of weird spots, right? E to the negative x. So here what I would do, if you multiply top and bottom by e to the x, fairly straightforward algebra trick. Then we'll have e to the x over, you have to distribute this e to the x to everybody down here. So 1 times e to the x is e to the x. 2 e to the x times e to the x is 2 e to the 2x. And e to the negative x times e to the x is 1, since it's going to become minus 1. You still have your dx. And that downstairs, write that in a slightly more suggestive order. That's 2 e to the 2x plus e to the x minus 1. Now, when you look at this, what do you want to do with that? What do you see showing up everywhere here?
Back to the bottom.
Sub, yes, but not for the whole bottom. The derivative of this whole bottom is a little too complicated, right? Like that would be 4 e to the 2x plus e to the x. And I don't have 4 e to the 2x plus e to the x up here to fuck with. Right? Remember, I need the derivative of the thing you're subbing for to make the sub go through. At least, most of the time. If you don't have that derivative of the thing you're subbing for, it's going to be hard to make the substitution work. Let me do one more sort of suggestive thing here. E to the 2x is the same as e to the x squared, like this. So I have 2 times that squared plus that minus 1. So staring at this, does anybody see a nice substitution?
E to the x.
Very good. I'll use the letter z just for fun. Let sub z equals e to the x. dz then is e to the x dx. So this e to the x upstairs, I'm going to group with this dx. That will be my dz. And then this is going to become a proper rational function. 2z squared plus z minus 1 dz. And from here, what do we do?
Sorry, what happened to the EX on the top?
He's going with the differential. So if you prefer to think of it like solving for dx, you can do that. 1 over e to the x dz is equal to dx. So when I plug in for this guy, there's a 1 over e to the x that's going to cancel this. Or you can think of it like you're going to group this with this. But so the e to the x upstairs is going away because the differential, the dz in my substitution, has an e to the x in it. I can show you the details here if we want. This is going to take a little more time. So I've got dx, which is 1 over e to the x dz. I've got the e to the x upstairs, and I've got 2z squared plus z minus 1 downstairs. The e to the x is here, cancel, cancel. And you get 1 over 2z squared plus z minus 1 dz. Same. So from here, what would we do? What kind of function is this? How do we handle it? Scaring me, little guys. How would you integrate this? Wrong answer is better than no answer. What would you want to try?
Factor by parts.
Factoring is good. Yeah, there's not really any way I could set this up by parts right now, but definitely we should try to factor this. Does this factor nicely? Yeah. I can write that as 2z squared plus 2z minus z minus 1 using my AC method, and then factor 2z from the start. And I have z plus 1 left. Factor -1 from the end. You have z plus 1 left. So this is 2z minus 1 times z plus 1. So this is integral of 1 over 2z minus 1 times z plus 1 dz. What do we do from here? Partial fractions now. All right, that's all we have time for, right? But you can make a little substitution in this integral to turn it into a nice simple rational function, a proper rational function. And the way we integrate proper rational functions is by factoring the bottom and doing partial fractions. This is not a hard partial fractions, right? This quadratic did factor, it's not irreducible. So I factor it and then set it up. You'd have a over this plus b over that, grind out a and b, and then you're home free. So if you want to get good at this stuff, you want to come into that test feeling like you can stomp everything, you're not afraid of any of it, here's the section, right? Spend a lot of time just solving these integrals. I would recommend trying to solve all of them if you feel so inclined, if you feel like you can. If you are willing to put in the time, making an honest attempt to solve all of these problems would be a really good way to review for the test. Of course, I'm not going to post all of these as homework. That would be brutal. The other things that I would recommend looking back at in preparation for the test is the chapter 6 stuff, the volumes, right? Everything that's in the study guide, really, you should remember to glance back at those sections. And if you feel insecure about cylindrical shells, come back here and work some cylindrical shells problems. If you feel insecure about the work stuff, go back and look at some of the work problems. But make sure that you're not forgetting the chapter 6 material, right? That is also a part of the test. All right, I got to get going. I got another class that starts here in just a few minutes, guys. I do have an office hour this afternoon from 1 to 2 p.m. You can also post to the Discord, send me a Canvas message. Remember, if you want to take the test in the testing center, you need to let me know that so I can reserve you a spot there. Otherwise, I'll assume you're taking the test with me online. And no matter where you're taking the test, you're going to need to scan your written work and submit it to that other assignment after you finish. The testing center people will probably not do that for you. You will probably have to do that yourself. You'll probably have to remember to do that yourself. So please don't forget, that is so important. The written work is the majority of the credit on those free response problems. And yeah, we'll talk about the test protocols, I guess, a little bit more on Friday. But that's it for today, guys. Take care.